Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. We are discussing an important topic, particularly reactivity of metallocene in this series of lectures on transition metal cyclopentadienyl complexes. To help explain the various reactivity patterns that are shown by metallocenes, in our previous class we have looked into the metal transition metal cyclopentadienyl interaction, particularly from their molecular orbital point of view. The electronic structure of the transition metal cyclopentadiene ligand interaction explained a lot about the electronic filling of these complexes. Also, he helped explain how the orbitals are arranged with respect to the energy, what are the conditions for their HOMO and the LUMO orbitals, and also greatly it helped explain the magnetic properties that arise from unpaired electrons present in the valence outer orbitals of this transition metal cyclopentadienyl complexes. Continuing further, we are going to discuss in detail more on the reactivity of transition metal cyclopentadienyl complexes, and the thing that stands out is their extremely facile reactivity with electrophiles. So, today we are going to talk about metallocenes, and to begin with let us just focus on ferrocene, one particular example ferrocene, like one particular type of metallocene, before we expand on the reactivity of metallocenes in general. Now, as far as the ferrocene is concerned, it is highly redox stable. That means that in ferrocene, iron is in +2 oxidation state and does not really undergo redox reactions to +3 or +4 oxidation states. So, this high redox stability ferrocene exhibits organic like reactivity. By this it means that this iron center is redox stable. As a result, the reactivity occurs at the CP ring. And that is why it gives this organic like reactivity. So, to help explain this point further, we are going to look at the reactivity of ferrocene, ruthenocene and osmocene towards various electrophilic substitution reactions. So, reactions. Let us illustrate this. In presence of an electrophile, the electrophile goes and attacks the CP ring, giving this cationic complex, this which eventually loses this proton, leading to electrophilic substitution on the CP ring. Now, this reaction is so facile that it reacts 3 into 10 to the power times 6 faster than in benzene, and the reason for extremely high reactivity nature of ferrocene, ferrocenyl CP ring towards electrophilic substitution is primarily due to its carbanionic nature. The facile reactivity is due to partial negative charge or carbanic nature of CP ring. Okay. So, these are sort of partially negative in charge because of its carbonic nature of the CP ring. That is what it makes ferrocene so vulnerable to electrophilic substitution reaction. So, this is an important reaction which distinguishes ferrocene from other transition metal complexes or other even organic compounds, is the fact that these reacts extremely fast with electrophiles, that is due to carbonic nature of the CP ring. So, as a result, this ferrocenyl amine ferrocenyl amine is more strongly basic than aniline. So, this carbonic nature makes this ferrocenyl amine more basic, significantly more basic than aniline. Similarly, ferrocenyl formic acid, this is called ferrocenyl amine, similarly ferrocenyl formic acid which is weaker acid than again benzoic acid. So, all it confers is the fact that these cyclopentadiene moiety are quite electron rich. They have this partial negative charge or anionic character. As a result, they make very strong bases and weak acids, and also they undergo electrophilic substitution reactions at a much faster pace than that of the organic molecules. Now, an important marker of this electrophilic substitution reaction, of course, is this Friedel-Crafts reaction. The Friedel-Crafts reactions sort of are taken to be a benchmark reaction for any kind of electrophilic substitution reactions, and no wonder that ferrocenyl compounds also exhibit Friedel-Crafts acylation reactions. So, ferrocene reacts with acetyl chloride in presence of AlCl3, giving both mono acylated, this is monoacylated product, and as well as diacylated product. Please note that the diacylated product occurs on the second ring and does not occur on the first ring where the monoacylated product has happened. One thing which sort of is an important point to consider that these electrophiles should not be acting as an oxidizing agent when undergoing electrophilic substitution reaction, because if it does, then that would oxidize ferrocene to ferrocenium ion. So, one important criteria is for electrophilic substitution reaction reaction, electrophiles should not be acting as an oxidizing agent, should not be acting as an oxidizing agent, as it would convert Cp2 Fe to Cp2 Fe plus or ferrocenium ion. So, this is an important criteria that has to be followed, or that has to be met when these electrophilic substitution reactions are covered, that they should not be acting as an oxidizing agent, because if it does, then ferrocene itself would get oxidized. So, if it does not act as an oxidizing agent, then obviously the electrophilic substitution reaction would occur, and then the question comes that where would the electrophile attack from, whether it will be an from the exo direction or from the endo direction. A common convention would however suggest an exo attack because of simple easier approach due to steric reasons, and indeed there are several experiments which does conclude the same insight or conclude the same attack. So, exo electrophilic attacks occur in the exo direction. The electrophile now this is best explained through this very sophisticated intramolecular acylation reaction, which further corroborates this exo attack in the electrophilic substitution reaction. So, that is beautifully illustrated in this particular example, which contain a 6-membered cyclohexyl ring attached to a CP ring. Containing CH2, CH2, CO2H, this when treated with CF3 CO2O reacts readily to give the product, which is from the exo direction, and that is reflected by this hydrogen in the endo position. Whereas the endo attack, as depicted by this reaction, which is extremely slow, so the exo isomer cyclizes faster than the endo isomer. and this is shown over here. So, this is a beautiful experiment which was done to prove the facial selectivity of the electrophilic attack, and it has shown that the exoisomer is formed faster, suggesting that the electrophile attacks from the exo direction, and which is also the conventional wisdom, because of steric reasons one may suggest that this exoisomer would attack much faster from the outer face of the CP ring than endoisomer. Another interesting reaction that we are going to be talking about is for the formation of a iron hydride complex because of this electrophilic reaction, but in this case the substitution reaction does not eliminate the proton, but in case results in the formation of iron hydride moiety. So, this is a nice variation of or nice variant of electrophilic substitution reaction which is predominantly seen for ferrocene. So, for example, the treatment of ferrocene with H plus sulfuric acid and acetic acid, CF3, trifluoroacetic acid, gives this expected protonated hydrogen complex. So, this is similar to the electrophile attacking the CP ring from a exo direction. However, what is interesting over here that one of the endo hydrogen of the CP ring shows an interaction with the transition metal which eventually will lead to the formation of iron hydride complex and this is a beautiful experiment in which this eliminating the H plus is actually grabbed by the iron, resulting in the iron hydride complex. This hydride complex has been characterized by proton NMR spectroscopy, where it appears upfield shifted at minus 2.1 ppm, and also characterized it by IR, where it appears as 1630 centimeter inverse this iron hydride moiety. So, this is an interesting example that showed that this proton when treated with acid, the attack indeed happens from the attack of the H plus indeed happens from the exo moiety, but the diene cyclopentadienyl cation so formed, the proton on the endo side get abstracted by the iron to form this iron hydride species, and the CP ring gets aromaticized and electrophilic substitution occurs. So, this is a nice demonstration of the fact that iron hydride can be formed through this electrophilic substitution reaction, and the hydride moiety has been characterized by proton NMR, where it appears upfield shifted at minus 2.1 ppm, as well as by IR, where it appears at 1630 centimeter inverse. Another important reaction, again the hallmark of ferrocene chemistry, is Mannich reaction. and these are also popularly called as aminomethylation. Reaction. The reaction is done under standard Mannich condition. Which is treatment of ferrocene with formaldehyde and a primary secondary amine in presence of acetic acid, which results in aminoalkylation or aminomethylation of one of the ferrocenyl CP rings, giving CH2 and CH3 whole 2. So, this again is an interesting reaction which occurs on the CP ring by treating ferrocene with formaldehyde and dimethylamine in presence of acetic acid. And this reaction, as mentioned, is called aminomethylation reaction. So, with this I would like to conclude today's lecture. We have been talking about various reactivity patterns of ferrocenyl complexes, and what comes to the fore is their extreme propensity to undergo electrophilic substitution reaction, and that is primarily due to the fact of its carbon anionic nature, which has results in a partial negative charge on the CP ring, which allows it to readily undergo these electrophilic substitution reactions. These reactions are so fast, about 3 into 10 to the power 6 faster than that of conventional benzene, exhibiting similar electrophilic substitution reactions. Also, because of its electron richness and a carbon ionic or partial negative charge on the CP ring, these aminoferrocenyl complexes are extremely basic than aniline, whereas ferrocenyl formic acid complexes are even weaker acids than benzoic acids. Having said that these ferrocenyl complexes undergo facile electrophilic substitutions, there are however certain restrictions, though the restrictions being that these electrophiles should not be interfering with the iron center. That means that electrophile cannot be acting as an oxidizing agent, which might convert ferrocene to ferrocenyl cation, and if it does, then this electrophilic substitution reaction would not occur. So, the primary conditions or restrictions on the electrophilic substitution reaction is that the electrophile should not be acting as an oxidizing agent. The second thing that we learned about this electrophilic substitution reaction is the approach of the electrophile or attack of the electrophile on the CP is primarily from the exophase of the CP, that is from outside of the CP or external face of the CP. That also is a conventional wisdom, because the endophase is more sterically crowded, and the approach of the electrophile from the endophase is not facilitated, and that is shown by two beautiful experiments by Rosenthal, where it was experimentally proven that the exocyclization occurs at a faster pace than the endo reaction. And lastly, we have seen as a fallout of this electrophilic substitution reaction, formation of iron hydride complex, as well as this aminomethylation or the Mannich reaction occurring readily on ferrocenyl complex. So, with this I would like to conclude today's discussion, and some more of the reactivity of transition metal cyclopentadienyl complexes we will dwell upon in the next lecture. Till then, goodbye and thank you.